Good morning, kiddos. This is basically just a review of what covalent bonds are, how to draw Lewis dot diagrams, and our first real steps into creating Lewis dot diagrams for covalent compounds. A lot of this might be a review. I just want to go through it so you kind of can see all of my notes put together and then walk through some examples. So first things first, big most important thing is knowing that covalent bonds are formed between two nonmetals, right? Ionic bonds were formed between a metal and a nonmetal. Covalent bonds should just come from basically well, if you look down at this periodic table, all of the red boxes, those are our nonmetals. So to draw Lewis dot diagrams, we are basically just drawing a simplified Bohr model. We're making things a lot easier for us. Instead of drawing all the circles and all the different levels of valence electrons, we simply draw the outermost electrons and use the symbol for a nucleus. So our steps in drawing Lewis dot diagrams are to look at the periodic table and determine what column are elements in, because this gives us not only, like the physical symbol because you're looking at it, but also the number of valence electrons. So columns are up and down. I tried really showing this here, but if we were looking at, say, selenium, right here in number 34, I would be able to look there and say, oh, okay, my symbol is going to be Se. And if I look at the top of my column, it's 6. So I'm going to have 6 valence electrons. And it's just a reminder of how to use the periodic table properly. So after you figure out the symbol and you figure out how many valence electrons you have, the next step is to write down the symbol and place the dots on the symbol in a clockwise manner, one at a time. So I'm going to just kind of put a little example right here if my iPad wants to work with me. So in this one, it'd be Se, and then we've got 6 valence electrons. So one at a time, clockwise manner. So I would do 1, 2, 3, 4. It's a little slow. And then we double up electrons. So has to be 1 on each side. So 5 would go here and 6 right there. And so that's pretty much how we do it. The next big thing I want to point out is that the solo electrons, those electrons that are sitting there by themselves, those are the ones that can and will form bonds. So if we again look here at selenium, we've got these two guys that are by themselves. So what we can determine from this, I know it's super weird, sorry, things go back and forth, is that selenium will form 2 bonds. And it has to form those 2 bonds to make a stable compound. Cool. So now let's put this off. And just remember that the goal of covalent bonding is to give every atom a full valence. Unlike ionic bonding, where one element basically steals all the electrons to themselves, the covalent compounds share their electrons equally. So it is the goal, and the purpose of it is to have every single atom, no matter if it's 2 or 17, to have a full total valence. So that was a review. Our goal now is to put all of that knowledge into drawing Lewis dot diagrams for covalent compounds. So I'm going to try and walk through these steps while giving an example as well. The compound that I'm first going to choose, let's do, I know it's freezing, silicon tetrachloride. So SiCl4. Now, first things first is we count up the total number of valence electrons for the atoms. So just going to go back to the periodic table really quick. Silicon is right here in column 4, so I know it has 4 valence electrons. Chlorine is in column 7. That gives me 7 valence electrons. So, no, there's a lot going on. Let's see if I can get this to go back on. Here we go. So, we just determined silicon gives us 4 valence electrons, and chlorine will give us 7. Now, chlorine, if we look at it, there's 4 chlorines there. So we don't just have 7 valence electrons from it, we have 7 times 4 valence electrons from it. So that should give us, if I did calculations correct, 32 valence electrons to mess around with. So I'm going to just zoom back in on there, 32. We've done that, we've counted all total available electrons. The next thing to do then is determine the number of bonds each atom can make. Whichever atom makes the most, we determine is the central atom. Now, there are a couple ways to figure out how many bonds. The easiest one, and that uses our skills that we just reviewed, is drawing the Lewis dot diagrams for them. So, since I've already determined how many valence electrons each gives, it's going to be really easy to do these Lewis dot diagrams. Silicon has 4, so it's going to have 1, 2, 3, 4 valence electrons around it, and chlorine with 7 valence electrons should have 1, 2, 3, 4, 5, 6, and 7. So now, bonds, or the number of bonds an atom can make, are determined by how many solo electrons they have around them. So in this case, we're going to get 4 bonds from silicon because all of them are by themselves. And for chlorine here, we're just going to have 1 bond. There's only 1 lone electron right there. Perfect. So that also allows us to kind of give a start to how we are going to draw this compound out. So I'm going to add 1 more note in here just so you can kind of see this process. Maybe. This guy is going to be our central atom. And that helps us, in number 3, arrange the atoms in the most symmetrical way around our central atom. So we're going to have silicon in the center. In symmetrical way, it's basically north, south, east, and west, right? You want a mirror image on both sides. So on top, I'm gonna maybe just draw this without the thing on there. So I'm gonna put chlorine, 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 and chlorine. Sorry about that, guys. I'm not paying for this app. Okay, so we have done arranging the atoms in the most symmetrical way. And then our next step for number 4 is just bond each of the atoms to the central atom with 1 bond. So I know that sometimes people like to do the 2 dots and then kind of circle them or draw a line through. I think it's way easier to remember, hey, a line equals 2 electrons, and that forms a bond. So I'm going to go back in the same one and just add in those bonds. So I've done with number 4 now. And really quickly, just because it helps, we did this determining of total electrons in number 1 so that we knew how many electrons we can put around this bond, or this, compound. So right now I have got 8 of my electrons in the compound. Each of those bonds, again, represents 2 valence electrons. So I have got a total, sorry, my iPad's totally freezing, total of 4 bonds. 4 bonds, 8 electrons. So now I've done number 4. Number 5 is to give a full valence to the non-central atoms first. So I'm going to go back through and give all of my chlorines the right number of valence electrons. This chlorine, let me just highlight so you guys can kind of see what I'm talking about. Right there, it's got 2 electrons around it, so it needs 6 more. So I'm going to add in 1, 2, 3, 4, 5, 6. And I'm going to just do the same with the rest of them because they all look identical. So just go back through. Not the prettiest dots, but very hard to work on an iPad. Okay, so I have done that. I've given all of the outer elements or the outer atoms full valences. Now, number 6 says put any leftover dots on the central atom. So I have to make sure I don't have any more or have any extra dots. So I'm just going to go through and count. And yes, it's that basic. It's going to be 2, 4, 6. I'm going to try and use a highlighter so I don't mark up this whole page. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have used up all of my valence electrons and we are totally done. Each of the chlorines has a full valence. If you look at silicon, I know there's so many colors going on right now. If you look at silicon, it has 8 valence electrons around it because it's sharing all those bonds. So every line means that it has 2 electrons, and so does the chlorine next to it. So we're totally set. We've got that all covered. And it means that we don't really have to worry about number 7 or 8 right now. Or excuse me, number 7. But I want to read through this one. So let's say we did what we just did, but the central atom doesn't have enough valence electrons, and we've used up all of the electrons available to us. That's when we start to move pairs of electrons off of our ligands, is actually what their names are, but those outer atoms, and put them into the central atom to give it a full valence. So normally what happens in these situations is you get a double or triple bond. So you don't just have to have a single bond, you can double that up, you can triple it. There are very, very few cases in which there's actually 4 bonds included in a compound. This also kind of calls into us, or reminds us to focus on the number of bonds an atom wants to have, because the number they want to have is the number they have to make. So really quickly, I'm going to go back through. We're going to do one more example, and it's going to be for carbon dioxide. So carbon dioxide, step number 1, total number of valence electrons. We get 4 from carbon and 6 from each of the oxygens. That brings us to a total of 16 electrons that we need to place around this molecule. Next is going to be determining the number of bonds each atom can make, and whichever makes the most. So carbon's giving us 4, oxygen gives us 1, 2, 3, 4, 5, 6. So we've got 4 bonds here and 6 bonds, 6 valence electrons and only 2 bonds on oxygen. That's going to make carbon our central atom. And fun fact, carbon will always be our central atom if that's a choice. Carbon or silicon, always central atoms. So I'm going to put carbon down, and I'm going to put oxygens around it in the most symmetrical way. So it can be top to bottom or left to right. I like left to right. Now it's bonding those outer atoms to the central atom with a single bond. Boom. I've got 4 of my electrons down. I'm going to give the outer electrons their full valence first. So I've got 2, 4, 6, 8, 10, 12, 14, and 16. Cool. All of my electrons are spread out. The oxygens have a full valence. But if I look at carbon, it does not have a full valence. There's no extra electrons to give to it. So that must mean that now I actually have to take from oxygen and put onto carbon. So I'm going to take this guy right here and move it in between. I'm going to do the same on the other side. And I'm going to just kind of write down here what happens. I'm going to put it right below. I'm going to take a little bit more space. So now it's going to look like this. And if we just look at that, you can see that we've actually done a lot better for this compound, because we've given carbon the 4 bonds it needs, and we've given oxygen the 2 bonds it needs. So we've satisfied that role. And then I'm just going to give the extra electrons to the oxygens and see if that helps. So we've got 8 total electrons. Let's do 10, 12, 14, and 16. Boom, satisfied all the roles. So now I'm just going to kind of give you the checklist on the bottom. Do all the atoms have the correct number of bonds? Yes, we did that. Do all atoms have a full valence? Absolutely. And did I use all available electrons and no extra electrons? Yeah, you can't just add electrons on, that's nonsense. So we use only what's available to us. The very last thing is that there are exceptions to this octet rule, right? Number of valence you can have is always 8. However, we have some times where that's not true. And that's going to be hydrogen. Hydrogen's a really big one, because we don't want a hydrogen to have 8 valence electrons, because its closest noble gas is helium, and that's only 2 valence electrons. So if we tried to give it 8, it'd be way too overwhelmed. So if you see hydrogen and it's just connected by a single bond, great, it has a full valence. You don't need to add an extra to that. And well, that's basically kind of the notes for how to do Lewis dot diagrams and how to use Lewis dot diagrams to help things bond. I will put up a copy of this on Schoology as well as teacher notes. And if you have any questions, just remember to stop by for office hours.